All right, it's time to start recording, and nothing changed on the display. I just need to assume that clicking on that thing did it. And all right, well, now if I go to this one little hidden box, it says my choice is to pause the recording, so it must be recording. Okay. This is the last day of our study of energy, and up through today's material will be what could be on the test. So now I am doing, actually, this first problem isn't too bad. It would be a potential test question difficulty on here. After on Monday, I'm planning on starting actually our unit on momentum, which will be on the final and not on another unit test. But sometime Monday, we'll have a couple of review sessions. You might try to make either one of those. Okay, so we have a driver in a car traveling at 28.3 meters per second when he drives from bare pavement onto packed snow and ice. In the road 83 meters ahead of the car, he spots a tree lying across the road. He immediately hits the brakes. He's fortunate to have anti-lock brakes, but the coefficient of static friction between his tires and the road is only 0.23. How fast will the car be going when it hits the tree? This might be similar to the situation the person driving 100 miles an hour through downtown Cheney ran into when they saw a car in front of them and they slammed on the brakes and skidded for 280 feet before having the collision. But we can do a calculation on this thing. So this will be an energy conservation problem. Sometimes we'll have the situation where the energy before will equal the energy after. But sometimes it'll be the energy before plus the change in energy will equal the energy after. And so if there's something that either adds energy to the system or removes it from there, and in this case, we'll have the energy lost to friction, and that's going to be a negative value. So oops. So that's what we'll have here. But in a lot of these problems, we won't have any lost energy, and we can talk about the energy before equaling the energy after. We've done some with springs where that was the case. Okay, well, before, the energy that's going to happen doesn't say anything about a tilted road, and actually I tilt the road in a repeat of this problem so we can see what will happen in that case. But that means we're on level ground. And so the only potential energy we've had so far is either a compressed or stretched spring or gravitational potential energy, where we might have a difference in height. And we don't have that here. So initially, all we have is kinetic energy. So we'll have 1/2 mv initial squared for the initial energy. Afterwards, we'll have some 1/2 mv final squared, and we're after v final. The change in energy, we need to figure out just how that's going to work here. And if we think about it, forces on the car, let's just assume they're headed to the right here. There'll be mg downward, a normal force upward on a horizontal surface. With no other vertical forces, the normal force is going to equal mg, and then we'll have a frictional force in this direction. In this case, it's kinetic friction because they're skidding. or no, it's static friction, excuse me. But it's a low coefficient of static friction. And so they are not skidding, they're using their anti-lock brakes. There is still a way to make your car go into a skid, although it's actually there are a lot of safety systems built into cars nowadays where if the car starts to sense that the wheel might be locking up, it'll do various things. I know that Toyota Prius that we had would do something like that where it kind of takes over. But I've seen people do something kind of dumb if they have a stick shift car and they might think that okay, I shouldn't jam on my brakes because the road might be slippery and I could skid. So instead, what they'll do is downshift, and that doesn't help. It's just like jamming on your brakes. Downshifting puts an internal force on the wheels to slow down their rotation, just like pushing on the brakes does. And it can actually cause you to overcome the friction between the tires and the road, which is the external force that actually stops your car. And we had a situation actually similar to this driving one time. We were driving from Pendleton, Oregon, over the Meacham Hill to La Grande, Oregon. We used to live in La Grande. And the road did something very much like this. All the way up the hill, it was bare pavement. And then we got just, let's see, actually up by Dead Man's Pass is what it's called. And the road went from bare pavement to packed snow and high ice in a very, just a few yards. And we were doing okay in our car. We had this stick shift car, and but we got passed by somebody in a little Honda something or other, one of the Honda sports cars. And as soon as they got onto the ice, it looked like they downshifted because all of a sudden they just lost complete control of the car. And they're right in front of us, just spinning around, bouncing from one snowbank on one side of the road to the snowbank on the other side of the road. And as soon as I saw that, I just pushed in the clutch. We had this ancient van with a stick shift and pushed in the clutch and was coasting as slowly to a stop as I could. And but they ended up just stuck in the snowbank over on the right side of the road eventually, and um, looked like no harm was actually done other than I don't know, they would have had their pulse rates going through the roof. But anyway, let's figure out what we've got going on here. How much energy will we lose to friction in this case? Well, the distance they travel is 83.0 meters while they're slowing down. And the work done by friction, W sub F, is what's going to go in here. And it's going to be negative. So we'll have 1/2 mv initial squared. And let's figure out that work done by friction. It's going to equal mu sub s times the normal force, that's the frictional force, times the displacement, but the frictional force is in one direction and the displacement is in the other. And so this is going to get a minus sign. So, and the normal force is going to equal just mg in this case. So we will have minus mu sub s mg d, where that's the displacement, that thing, and that'll equal 1/2 mv final squared. And that's the only equation that we have to solve on this problem. So not too bad. Now, first thing, I recognize that there's a mass in every term, so I can divide that out. It's V final that I'm going to want, so I'm going to get rid of the 1/2 by multiplying everything by 2, and that will give me V initial squared minus 2 mu sub s g d equals V final squared. And if I solve for V final, it's just going to be V final equals that square root of V initial squared minus 2 mu sub s GD. And now I may as well plug the numbers into that. But this isn't a bad thing to have to solve. And so these energy methods can be pretty darn powerful. Okay, let's see. Initial velocity was 28.3 meters per second minus 2 times that coefficient of friction, 0.23 times g, 9.81 meters per second squared, times the displacement, 83.0 meters. I'm just kind of doing this in my head here. This is going to be a bit less than 900. Let's see. I don't know what this is going to be. We'll have to figure out that. Actually, we may get an imaginary number. Oh, I forgot about the 0.23. Okay, so that's going to make it quite a bit smaller. But we'll see. Maybe they're nearly stopped. And this will be down to 1 sig fig. We may be down to just 2 significant figures here at the end, I think. So, yeah, so I would just call this 21 meters per second at the tail end, because I've only got 2 sig figs on that coefficient, and that's going to knock down the precision of this one, which will knock down the precision of the difference between the two. So, and actually 21 meters per second times they're still going about 46 miles an hour. And so that's pretty fast. And they're going to run into the tree at that speed. So it'll do some damage to their car. So you have to be really careful when you're driving on slick surfaces. Okay. Any questions on that one? This ended up not being bad at all when we actually plug in the stuff, but you have to know how to write down this, and you have to know how to calculate the work that's done by the friction. So you need to know that. We could have thought of this as a work kinetic energy problem as well, and say the change in kinetic energy will equal the work done, and it would have set up to give us exactly the same equation. So, okay, well, let's go on to this other complication that I thought of tagging on to this problem. This time the car is on a road that slopes upward at 2.20 degrees in the direction the car is traveling. So that's a pretty small slope. And so we'll have something that looks like that. This is way exaggerating a 2-degree slope, actually. But if I made it a 2-degree slope, it would be about impossible to have anything on there. However, there will be this 83.0 meters between them and the tree that's down in the road, and that just looks like a log in cross section. So we'll have that, but there'll be an altitude change as a result of that. So we're going to have some potential energy built into this problem, gravitational potential energy that the other one didn't have. And also, because it's on a slope, things won't quite be so simple anymore as far as calculating the frictional force. Let's see, we'll have mg downward. And here's our 2.20 degree slope. And the normal force is going to be up in that direction. And then the frictional force will be down the hill here. And that friction force is going to do negative work on the system. Now, mg will also do negative work on it, but we're going to take care of that by thinking about the gravitational potential energy, and we'll just have a change in altitude for that. So that's something that we'll have to deal with. Okay, this is 2.20 degrees, which I'll call theta. This angle here will be 90 minus theta because these two are at right angles, but these two are at right angles. So that makes this thing theta again. And the component of g that's down the hill will be mg sine of theta. The component of mg that's into the road surface will be mg cosine theta. So if I was to quickly invent a tilted coordinate system here with x pointing that way and y pointing that way, the sum of the forces in the y direction are going to equal 0 because there's nothing happening. It's not jumping off the road and it's not sinking into the road. So n plus mg is 0, or n minus mg in scalar form, mg cos theta, excuse me, mg cos theta, n minus mg cos theta will equal 0. So the normal force is mg cosine of theta. So it just changes a little bit. All right, well, what we'll have is initial plus change equals final. The change in energy is going to be, in this case, the energy lost to the friction. And so the initial, all we're going to have, I'm going to let the 0 of gravitational potential energy be at the initial position. And so all we'll have to begin with is the 1/2 mv initial squared. Whoops, the change is going to be minus the frictional force. In this case, F sub s is mu sub s n. In this case, n is mg cosine theta, so F sub s is going to be mu sub s mg cosine of theta, and the work done by friction, W sub F, will be this times the displacement. But again, there in the force is down the hill, the displacement is up, and so it'll be a negative amount of work, mu sub s mg cosine theta. Okay, well, tag that on here, mu sub s mg cosine theta. So the only difference on the left side is that we have to have this cosine theta on here because the normal force is a little bit less than it would be if it was just a horizontal surface. And the cosine of 2.2 degrees, remember the cosine of 0 is 1, and at 2.2 degrees, it's just going to be a smidgen less than 1. In fact, yeah, the cosine of 2.2 degrees is 0.9993. So it may not even show up in the calculation as far as the difference there. Now, the final energy is going to be some 1/2 mv final squared. Okay, that's the final kinetic energy, but there's something else that it has, and that is if I let h be the elevation difference between the initial position down here. And the final position, we'll have some gravitational potential energy here of mgh. So we have that built into here as well. Okay, well, let's barricade off that. I think we can proceed as we did in the last one, except our terms are somewhat more complicated, although this one really doesn't, the cosine theta is not going to make a whole lot of difference on here. But if I, first of all, get rid of all the m's and then multiply everything by 2, I'll have v initial squared minus 2 mu sub s mg cos theta, whoops, got rid of the m's, is equal to v final squared plus 2gh. This thing was supposed to have a d on it as well. Let's see. Yeah, the work done by friction had the displacement on there. So that belongs here as well. Okay, so I've got a d and an h on here. D is the 83.0 meters. All right, kick that across and solve for v final squared. It's going to equal v initial squared minus 2 mu sub s g, I'll just write g d cosine theta minus gh. Okay. Yeah, and unit-wise will be good. G times h, that'll be meters per second squared times meters, which is meters squared per second squared, which is good for a speed squared. And then I've got a GD, which also is meters per second squared times meters. And this is dimensionless, and this is dimensionless. So it's just a matter of getting in the numbers here. And I think I'll just do it right in one fell swoop. The initial is still 28.3 meters per second squared minus 2 times mu sub s 0.23 times 9.81 meters per second squared times 83.0 meters minus 9.81 meters per second squared times h, which I hadn't actually figured out yet. H divided by 83 is going to be the sine of 2.20 degrees. Might as well figure that over here. So 83 sine of 2.20 degrees. And it's not much. It's 3.19 meters. But somehow I have to fit it into here. But that's it. Now it's just plug and chug on that calculation, which is complicated. You got to be careful sticking that stuff in there. But we had pretty much the only complications here were we had a cosine theta on the normal force, and we had a gravitational potential energy term. But still, this isn't terrible. This is easier than solving those two-dimensional Newton's law problems. So anyway, we'll figure out how fast they're going in this case. Did I miss a cosine of theta on here. Cosine of 2.2 degrees. I did. Whew. That's a lot of stuff to plug in. Okay. To two significant figures this time, I get, let's see, I don't remember what I got on the last problem. Oh, I got 21 meters per second. I get 2.0 times 10 to the first meters per second. I don't remember how many miles an hour I said 21 meters per second was, but 20 meters per second is just about 45 miles an hour. So still going at a pretty clip when they hit the tree, even though they were going uphill, but it wasn't much of a hill. So there we have it, a more complicated problem. Okay, I think this may be the last one I was going to do today. Yeah, I've just got a couple of sketches on this one. This one's complicated though, and let's see just what happens. This is one that's out of the book that I want to use next quarter. We'll be studying completely different material than this, but it's got some nice stuff. Anyway, we have a 2-kilogram package up here, released on a 53.1 degree incline, 4 meters from a long spring with a force constant of 120 newtons per meter that is attached at the bottom of the incline. And the coefficient of friction between the package and the incline are mu sub s equals 0.40 and mu sub k is 0.20. The mass of the spring is negligible. What is the speed of the package just before it reaches the spring? So when it's traveled the 4 meters down here, that part of the problem is going to be very similar to the problem we just solved. But then it asks, what's the maximum compression of the spring? And the package rebounds back up the incline. How close does it get to its initial position? So, okay, so we want to know how much will it compress the spring by in the part B. And part C is how far back up the incline is it going to get? So this is kind of complicated stuff, which is why I give ourselves a second page where we can reproduce some of this stuff on with the drawing on there as well. So let's see where we go. For part A, all right, we just want to know the speed when it gets down there. Well, we do have friction acting, so we're going to have some initial energy minus, I'll just call it the loss to friction this time, is going to equal the final energy. Now, we've definitely got an altitude change on here. And so if we're using an energy solution, we have to take into account gravitational potential energy in this case. Well, I'm going to select just sort of arbitrarily the point of contact where the mass will hit the spring as where U sub G, the gravitational potential energy, or U sub grav, you can call it whatever you want, that's where it will be equal to 0. So it's going to have some gravitational potential energy as part of its initial energy. In fact, that's it for initial energy because it's released from rest, I think. Let's see, it's released anyway on this incline. So that means we're holding it up there and then we let go. We release it. So to start with, all we're going to have is gravitational potential energy. I need to draw myself a little sketch here. The hypotenuse is going to be the 4.00 meters. Oh, isn't it 2GH? Kyle, let's see. Did you catch something? Yes, it is. Okay, so it's not going to be going as fast. All right, made a mistake. Oh, I think I can call that calculation back up. Yes, I can. Okay. Thanks, Kyle. I go into insert mode. I just need to go, oops, nope. I want to go ×2. Okay. Okay. So it's only going 19 meters per second. That made a little bit of difference. So not quite 45 miles an hour. It'll only be about 42 point something or other miles per hour. So still pretty substantial collision between a car and a tree, depending on the size of the tree. Okay, so initial energy minus that loss to friction will equal the final energy. And this is just sliding down the thing to this point. And what will we have? Initial was just, oh, here's where we are, 53.1 degrees. This will equal 4 meters times the sine of 53.1, because this height divided by the hypotenuse is equal to the sine of 53.1. So I calculate that. Is 3.20 meters. Okay. So for starters, and I'll just call that H, so I don't have to write it down again. The initial energy is just going to be mgh. The final energy is going to be kinetic energy. It has no more gravitational potential energy, so it'll be some 1/2 mv final squared. So all I have to do here is figure out the loss to friction. Well, we learned on some previous problems, although it's good to redo the thing, that for a free body diagram, we've got mg acting downward. And I keep drawing it in a way that gets in the way. Actually, I'm going to do that over again. Here's mg. We'll have friction down the thing like that. So there's our force of friction, and in this case, it's kinetic friction. We've got this thing that's inclined at the angle theta, and we'll have the normal force perpendicular to that. So those are the three forces that are acting. Whoops. It's going up the plane, not like the last problem. So the kinetic friction is going up the plane, resisting the sliding down. However, what we're interested in is the components of the weight, because the component that's into the plane, which you could probably guess what it's going to be this time, is going to be balanced by the normal force, and that's the one that'll tell us how big the normal force is. So anyway, there's theta. Here's 90 minus theta, and here is theta again. And that means this is theta, that little angle there. And this divided by mg will equal the cosine of theta. So the part that's into the plane is mg cos theta again. And if I consider the sum of the forces in some y coordinate system, if x points that way and y points that way, they're going to equal 0 again. It's not jumping off the thing and it's not sinking into the plane. So n minus mg cosine theta is equal to 0. And you may notice a pattern on a lot of these things that we've had that being the case before. So the loss to friction will equal the frictional force. It's mu sub s times n, but in this case, n is mg cos theta again. So minus mu sub s mg cosine of theta times the distance that that thing acts over. And this time I'm just going to write it as 4.00 meters. So there we have it. Let's see. Every term has an m again, so this isn't too bad. Unfortunately, that won't be the case on part B or C. So those could be kind of complicated. We've seen something like this before. Multiply both sides by 2 and V final squared will equal 2 times the quantity GH minus mu sub s g cos theta times 4.00 meters. And I multiplied everything by 2. So now I just take the square root. And this one's not as bad as the last problem as far as that goes, but we'll see how things go here. The final is going to equal square root of all that junk. 2 times let's see, h was 3.20 meters. Minus mu sub s is, why did I put mu sub s? Yes, Cooper, it would be mu sub k, not mu sub s. So okay, at least I didn't punch any numbers in this time. So mu sub k is 0.20 times 9.81 meters per second squared. I keep running out of room. Oh, well, I can kind of cheat onto the something or other, this other thing. 9.81 meters per second squared. Oh, the cosine of 53.1 degrees. This is going to be substantial this time, or substantially less than 1 anywhere. And then times the 4.00 meters. And I have to finish off that parentheses, so I make sure that I multiply everything by the 2. Okay, let's see. I guess I'll just grin and bear it. Getting kind of tired of these calculations. Okay, 2 times 9.81. So that's in parentheses, minus 0.2 times times cosine 53.1. Hopefully I did this right. You can check on it. I get 7.3, and we can probably only keep 2 significant figures here. Meters per second. Let's see, unit-wise, that'll be correct. Unit-wise, that'll be correct. Yeah, so the units are all right. So 7.3 meters per second is, I don't know, this is kind of an artificial situation, so it means more when you've got a car running into a tree, I guess. But in this case, that'll be the speed that it hits the thing at. So let's start on part B on this page, and then we'll continue it on the second page here. For part B, I would like the initial energy just to be the kinetic energy that it has right here. Again, we'll go with U gravity is equal to 0. And so we'll have that. And I'll start with 1/2 m, I'll call it V final squared. Oh, and this will be my initial energy minus the loss to friction. And that will equal, what are we going to have at the end as far as energy is concerned? Well, we're going to have a spring that's compressed by some distance x that we don't know. And so we'll have this initial energy minus the part you lose to friction is going to go into 1/2 kx squared, but we're also going to be lower than the spot where our gravitational potential energy is equal to 0. So we're going to have negative gravitational potential energy here. So minus mg times some distance. Well, if it compresses the spring by a distance x, and it started off up here where U grav is equal to 0. This is 53 point whatever degrees it was, 53, 1 degrees. I'm curious about that. Yeah, this is approximately a 3, 4, 5 right triangle, except this length is 4. So I don't know, that's just a little bit weird here. But anyway, that's the angle in that. And this would be, this distance divided by x would be the cosine of that. So this would be x cosine of 53.1 degrees. So times x cosine of 53.1 degrees. Okay, well, what about that loss to friction? We're still going to have the frictional force, in this case being mu sub k mg cosine of theta, but this time, instead of having a distance 4.00 meters, we're going to have a distance x. And so this will end up being mu sub k, kinetic energy, mg cos theta times, actually, x. Yeah, it's just x that goes on here. Okay, well, that's a pretty complicated expression that I'm going to have to copy down onto the next piece of paper here. So let's make sure we've got it right. We have 1/2 mv squared minus mu sub k mg cos theta. That's the magnitude of the frictional force. And if I multiply that by x, that's the force times distance, and it's a negative contribution because the displacement is down and the frictional force is up. And stealing stuff from the, that'll equal the potential energy of the spring when we compress it by a distance x, 1/2, minus mg x, which is actually, or mg times x cosine of 53.1, because we want the amount that it's lower than where it started from. And that's what that is. So isn't this a nice looking little thing? Okay, we have a number for this, so that won't be too bad. We can turn this into a number. And we actually have to include the mass on this one because this term has no mass in it, although we can actually divide everything by m and have one term that has k over m in it. Let's see. Oh, yeah, k is 120 newtons per meter, so we can do that. And then we won't have m's. So let's get rid of the m's first, and then maybe bring everything over to the right side of the equation. So, but what I'll bring over is everything without the m's, and I'm going to put an m right there. So on the right side of the equation, we will have 1/2 k over m. Let's see, minus that gx cosine of 53.1 plus this term here, which is mu sub kg cosine of theta times x. So I've got two terms with x in them, and then minus 1/2 v squared. And I was supposed to have a 0 equals there. Okay. And also this was supposed to have an x squared on it, right? Thought something was missing. Okay, well, this is a quadratic equation. This will be the coefficient on the x squared term. Let's see. If I factor, actually, I'm going to reverse the order of these two and put the x at the end. So I'll have mu sub k g cos theta minus g x or g cosine of 53.1. Oh, that's theta again, isn't it? Was it really that simple? Okay, I shouldn't have reversed the order on that, but we'll find out why. This is also g cosine of 53.1 degrees. Okay, and then I will have the minus 1/2 v squared at the tail end. Now, I definitely don't want to solve this using the quadratic formula where I'm going to be sticking the stuff in there. But what I'm going to do is just calculate each coefficient here. So 1/2 of k over m, or k over 2m, is going to be 120 divided by 4. It's a 2 kilogram package. So, and so I get 5 point. Actually, I only have two significant figures on the spring constant. So 5.0. Now, a spring constant is a Newton per meter, and I'm dividing by kilograms. So I'd be newtons over kilogram meters, but a Newton is a kilogram meter per second squared. So the units of this thing are actually per second squared. And I'm going to write that as second to the minus 2 times x squared. There's one coefficient. Plus, And I think this one's going to be negative the way that I ended up writing it. But I've got g cosine of 53.1. It'll be negative. All right. Times mu sub k minus 1, actually. Yeah, I get minus 4.7. And the units on this are going to be meters per second squared. And I'll be multiplying that times x, which will be measured in meters. And if you look, notice here, I'll have meters squared here. This is actually 1 over second squared. So this term is actually meters squared over second squared. This will be meters. So it'll be meters times meters per second squared, which is also meters squared per second squared, minus 1/2 times, this was supposed to be v final squared, wasn't it? Yeah, all the way through v final. And it's that speed that we figured out in the first one, which was 7.3 meters per second squared. Okay, so 0 is equal to that. So it's time to plug these numbers into my program solver. And if you haven't downloaded a quadratic equation thing to your computer or your calculator yet, you should probably. So anyway, the x squared term is going to be 5.0, not that the program cares. This term is going to be minus 4.7. And this term is 7.3 divided by 5. I'm going to punch in 3 minus 3.65, but I know that there's only two significant figures when I'm done. So minus 3.65 anyway. Yeah, that should be right. And I get a negative root and a positive root. Let's see, how would that positive root or the negative root make sense? It actually doesn't in this case, I don't think. Let's see. Yeah, I've been treating x as a positive number here, kind of down the plane in a weird way, maybe a sloppy way. But I'm going to go with the positive root here that x is 1.4 meters. Let's see. That will give me a value of 0. Yeah, and if I was having x be negative down the plane, I would have had to reverse signs on these things. So I was treating x as a distance. Okay, so that's that part. Now, that's only 2/3 of the way through the problem, although I don't know if I can finish off this thing. It then rebounds back up the incline. Oh, how did we get 5 for the 1/2 k over m? K is 120. So k over 2m is equal to, I think it was 120. Actually, it may not have been 5. I don't know what I was thinking there. Oh, I'll tell you why. Because I meant to type in 120 divided by 4, and I missed the 1. Oh, rats. Well, that'll make a difference, but I think I can fix that. 2 times 2.00. 120 divided by 4 is actually 30. So if I revisit my calculation there, let's see. So this should have been 30. Does that answer your question, Caitlin? Oh. Wow, today's my day for making mistakes. I'm glad you guys are on top of this because otherwise we'd be sunk. Anyway, this should have been 30 and minus 4.7 and minus 3.65. So let me recalculate it. And, oh, let's see, program. Okay, A is minus or 30. Still minus 4.7. And still minus 3.65. Okay, this time I get a more reasonable value, I think. X is 0.44 meters. Okay, so it doesn't compress it by a whole lot, but it also, it was going pretty fast. It's a pretty stiff spring, actually, is what we have. And we're losing more energy as we go. Okay. All right, and the last part, which maybe we can take on. Let's see. Now it rebounds back up the incline. How close does it get to its initial position? I'm going to start over again with consideration of things and figure that we've got a spring here that's got energy stored in it. So initial, and we have a stopped mass. So initially, all I'm going to have is some energy stored in that spring, which is the X that I had last time. The X equals 0.44 meters. And it's that X. That's what we start with energy-wise. And I'm going to make the gravitational potential energy equal 0 here. Or do I want to do that? Let's see. Oh yeah, it's going to ask how close does it gets to its initial position. So if we have, I'm going to call the distance up this thing y this time. And this x is just a number. So we're going to go with that. U grav is equal to 0 there. We'll figure out how far from this thing it gets up there, recognizing that the initial position up here is 4.41 meters. Remember, it was 4 meters from the initial position down to the spring equilibrium position. And then we went another 0.41 meters beyond that. So we're going to get some distance y up here, and we'll subtract that value of y from 4.41 meters, and that'll be how far it is from the initial position. Then we may not have time to quite finish this, but I may just keep going on the recording, and if you have to run off to a class at 1, that's fine. Okay, where are we here? The initial energy we have. We'll have lost energy to friction again, which this time I'm going to write it as, it's again mu sub k mg cosine theta. Okay, that is the frictional force, and the distance it's going to travel back up the hill, I'm going to call y. So that's our lost energy. Now, what will we have at the end that we don't have now? What we're going to have is some gravitational potential energy. And this one isn't too bad, because here's our 53.1 degree angle again. Okay, I won't have any spring potential energy. I won't have any kinetic energy at the end. All I'm going to have is some height above this initial position here. And this height will equal, this divided by y will equal the sine of 53.1. So this will equal y sine of 53.1 degrees, and the gravitational potential energy will be mgy sine of 53.1 degrees. So this isn't such a terrible problem after all. Kick this term across and I'll have 1/2 kx squared equals mu sub k mg cos theta times y plus mgy sine 53.1 degrees, and that's theta is 53.1 degrees, so that's okay. But each of these terms has a y in it, so I'll have y times mu sub k mg cosine of, I'm going to write 53.1 degrees this time, plus mg sine of 53.1 degrees equals 1/2 kx squared. So I'm going to be dividing by that whole mess there. I guess it might be easiest if I just leave that up on top. Yeah, I think I will. Divided by that mess. Mu sub k mg cosine of 53.1 degrees plus mg sine 53.1 degrees. And this was stuff from another part of the problem. Okay. Actually, there's nothing left except plug and chug on this. Remember, we know x, it's 0.44 meters. We know k, that's the spring constant. And so this is all just a number. In fact, this entire right side is just number. Let's make sure the units are correct. This will be joules. So I'll have joules on top and newtons on the bottom. No, is it newtons? Let's see. Yeah, I think so. mg is kilograms times meters per second squared. So maybe I can think of this as a kilogram meter per second squared, but a joule is a kilogram meter squared per second squared. And everything's the same, except on top you've got a meter squared, on the bottom you've got a meter. So you'll end up with meters for units, which is good because we're solving for a distance. And when you get that distance, subtract it from 4.41, and that'll tell you how far short of the initial position you stop. So I'm not going to bother to calculate that here. Are there any other questions? Did I make any more mistakes on this one? I think I caught them all for this part C here. So we should be good. Okay, in the next day or so, I'm going to be posting some review material for test 2. And one thing I'm going to do is go through the book and pick a bunch of practice problems that you should do. And when I write the test, is it 4.44? Oh, when I fixed it. Yep. Yeah, 4.44. But anyway, when I write the test, I'm going to look at some of those practice problems and write questions that are very similar to them. So if you can do all those practice problems, you'll be in pretty good shape for the test. So I'll also have some probably one or two conceptual questions on the test where you'll have to write a paragraph of explanation on something. So I may try to put some of the questions out of the back of the chapter book or out of the chapters that we've studied on there as well. And I also want to put up some kind of a survey this weekend. I used to use SurveyMonkey, and I think they charge for everything now, but maybe I'll just have you fill out a form or something and let me know when on Monday afternoon or evening you would be able to make it to a review session. And then I'll select an hour in the afternoon and an hour in the evening when we could have a review session. Because I know, and you don't have to go to both review sessions, just one. And I'll also be posting a list of topics for the test and a sample test from some previous year. So I'll have all that stuff. And anyway, that's keep an eye out for that stuff showing up, and it should be soon. And I'm going to stop recording here and see you all Monday, Zoomily, I guess.